Trigonometric functions, unit circle approach. So chapter 6, section 2. So here's a unit circle. Basically, the idea of a unit circle is that the radius of the circle is exactly 1 unit, or we just say 1. Which means, as you can see from this little picture here, that when you're on the x-axis, you're going to cross at the point 1, 0 and negative 1, 0. On the y-axis, you're going to cross at the point 0, 1 and negative 1, all assuming, of course, that you're at the origin. But the main purpose of a unit circle is that it makes, as you can see with that dashed arrow, it makes the radius equal to 1, which means if we were to build a triangle to any point on this circle, it would have a hypotenuse of 1. So this is going to talk about the trigonometric functions, and let t be a real number and let p be a point on the unit circle at x, y, and that's the point that corresponds to t. The sine function then becomes the sine of t is equal to y. The cosine of t is equal to x. The tangent of t is equal to y over x. The cosecant of t is equal to 1 over y. The secant of t is 1 over x. And the cotangent of t is x over y. So let's look at this unit circle and look a little closer. Well, if you look at what we just said, we said that sine of t was equal to x and the cosine of t was equal to y. Therefore, any point on this unit circle is going to be at cosine t, sine t, since cosine t is equal to x and sine t is equal to y. And you're going to have a radius of 1. T being the angle. So if theta is equal to t radians, so basically if we're measuring theta in radians, the 6 trigonometric functions of the angle theta are as defined. Sine theta is equal to sine t, cosine theta is equal to cosine t, tangent theta, tangent t, cosecant theta, cosecant t, secant theta, secant t, cotangent theta, cotangent t. So we're just replacing t with theta, which theta is quite often used to represent an angle. Another one that's commonly used is phi or phi, generally used for a phase shift, but theta is very commonly used for the measurement of an angle, especially when you're dealing with trigonometric functions. So the first angles I want to talk about with this are what we call the quadrantal angles. And just to give you a little preview of that before I go to the next slide, you see that when you're dealing with the Cartesian plane, this xy axis, that you've got these lines, the x-axis, the y-axis. Any angle that puts you on one of those axes is called a quadrantal angle. So as we can see here, if we look at the second column in degrees, we see that at 0 degrees, because remember, you always start at the positive x-axis and then work your way counterclockwise. So at 0 degrees, 90 degrees, 180 degrees, or 270 degrees, and 360, of course, putting you back to 0. Those are your quadrantal angles in degrees. And then in radians, that's 0 radians, pi over 2 radians, pi radians, 3 pi over 2 radians. Now, I will make a clarification, in case I haven't done this previously, that when you're talking about angles in degrees, we tend to put the degree symbol, but if we're talking about angles in radians, we just don't put a degree or anything with it, and that represent radians. It's kind of like when you take the square root of something, you don't put the index of 2. Same thing here, when you're dealing with radians, if there's no unit included, we assume that it's radians. You could say 0 rad, pi over 2 rad, pi rad, 3 pi over 2 rad. Both are okay. Now you can see that I've given you your 6 trigonometric functions here: sine, cosine, tangent, cosecant, secant, and cotangent. And I've given their values at these quadrantal angles. And obviously we can see that just by looking. Sine is going to be the y value. So when we're at 0 degrees or 180 degrees, obviously we're on the x-axis, so y is going to be equal to 0. Whereas at 90 degrees, y is equal to 1, it's at its peak. If we're at 270 degrees, y is equal to -1, lowest value. Cosine, we can see the same thing, that cosine is the x value. So x is going to be equal to 1 at 0 degrees. It's going to be on the y-axis or at 0 at 90 degrees, -1 at 180 degrees, and 0 again at 270 degrees. Now, all these other ones we can see are related to it. Tangent is 0, not defined, 0 and not defined at the respective angles. Cosecant not defined, 1, not defined, -1. Secant 1, not defined, -1, not defined. And cotangent not defined, 0, not defined, 0. So we have those angles. And it's really just a matter of looking at that unit circle and saying, well, is it 0, 1, or -1? And then plugging it into these values. And remember, all of these trigonometric values come off of SOHCAHTOA, right? Sine is opposite over hypotenuse. Cosine, adjacent over hypotenuse. Tangent, opposite over adjacent. Cosecant, hypotenuse over opposite. Secant, hypotenuse over adjacent. Cotangent, adjacent over opposite. Right? So if we plug in these zeros and ones, we get these values. So those are the quadrantal. Good to know, not that hard to figure out. Now, standard angles, we refer to the angles 30 degrees, 45 degrees, and 60 degrees, or pi over 6, pi over 4, and pi over 3, respectively, as the standard angles. Now, obviously, if you've got 360 degrees of angles, or 2 pi radians, there are an infinite number of possible angles. But we consider 30, 45, and 60 to be the standard angles. And as you get used to it, it makes sense, and we'll see things that'll make that fit in a little better. So standard angles, the trig functions for those angles are given here. And I will warn you that many calculus professors will expect you to know that the cosine of 30 degrees is the square root of 3 over 2. They'll expect you to just know it right off the top of your head. So if you have the ability to memorize this table, then that's great. And it'll give you a definite advantage when you walk into those classrooms where that is what is expected. So we can see here that for 30 degrees, we have going sine through cotangent in this order, 1/2, the square root of 3 over 2, the square root of 3 over 3, 2 square root of 3 over 2, square root of 3. For 45-degree angle, you've got from sine to cotangent, you've got square root of 2 over 2, square root of 2 over 2. Tangent is 1. Cosecant square root of 2, square root of 2, 1. And then for 60 degrees, you've got square root of 3 over 2, 1/2, square root of 3, 2 square root of 3 over 2, 2, and square root of 3 over 3. Now, I'm not one who really memorizes things that well. So to me, memorizing these and knowing them has always been difficult. So I'm going to show you standard angles the easy way. And this is how I'm able to find the standard angles without having to use a calculator, without having to memorize all those things. I go back to the basics. So I'm going to start with the 45-degree angle, standard angle, because it's really easy to work with. First of all, if I have a right triangle, then I know that the sum of the other two angles has to add up to 90. So if one of them is 45, the other one's going to be 45. So we have an isosceles triangle, which means two sides, the two sides opposite those 45-degree angles, are going to be the same length. So the simplest thing we can do with that is we can say, well, let those sides be equal to 1. So I've got two sides that are both equal to 1. And then I can use Pythagorean theorem to find the length of the other side. It's a squared plus b squared is equal to c squared. So 1 squared is 1, plus 1 squared is 1. So that's 1 plus 1 is 2. So the other side is going to be the square root of 2. So we have our hypotenuse. So with that, very easy for me to put that together. 45-degree angles, okay, 1, 1, square root of 2, the easiest thing I can work with. And then I can find all of those trigonometric functions from that. If I want sine, that's opposite over hypotenuse, 1 over the square root of 2. Now, realize that we do like to rationalize denominators. We don't like to leave a radical down there. So that means we multiply the top and bottom by the square root of 2 to get the square root of 2 over 2. Cosine is adjacent over hypotenuse. Again, 1 over the square root of 2, giving us the square root of 2 over 2. Tangent, opposite over adjacent, 1 over 1, which is equal to 1. Cotangent, adjacent over opposite, 1 over 1 is equal to 1. Secant, hypotenuse over adjacent, square root of 2 over 1 is equal to the square root of 2. And then cosecant, hypotenuse over opposite, square root of 2 over 1, or the square root of 2. So I can build all those easily enough from a triangle that I can just quickly sketch on a piece of paper and have my trigonometric functions for the standard angle of 45 degrees. Now that was the quicker, easier one, but I'm going to continue on. Find that 30 and 60 degrees aren't much harder to deal with. Luckily for us, if you have a right triangle and one of the angles is 60 degrees, the other one's going to be 30 degrees. So that works out nicely. I always put the 60-degree angle at the bottom and the 30-degree angle at the top. And by doing that, it allows me to build this triangle with the lengths of the sides as easy as 1, 2, square root of 3. And I can remember that 1, 2, square root of 3, because I can remember 1, 2, 3, simple enough. And once I will draw that in, I realize, well, wait a second, the hypotenuse has to be the longest side. So therefore, 3 is the one that's got to have a square root on it. So pay attention to that again. 1, 2, 3. And then we know the hypotenuse has to be the longest side. One of them is going to get a square root. Well, if I take the square root of 2, that's going to make it a smaller side than 3 would be. If I take the square root of 1, then 3 is still going to be bigger too. So 3 is the one that's got to have the square root on it. So now that I have that, I can start building all my trig functions. Now, please take note that 30 degrees is at the top. It's the top angle, which means opposite is going to be the 1 and adjacent is going to be the square root of 3. Hypotenuse will still be 2. But that comes into play as we do this. So we're dealing with a 30-degree angle. The sine of 30 degrees is opposite over hypotenuse, 1/2. The cosine of 30 degrees, square root of 3 over 2. Tangent of 30 degrees, 1 over opposite over adjacent, right? 1 over the square root of 3, which rationalized gives me the square root of 3 over 3. Cotangent, square root of 3 over 1, square root of 3. Secant, 2 over the square root of 3, which rationalized is 2 square roots of 3 over 3. And then cosecant, 2 over 1 or 2. So that's not too bad. And then 60 degrees works the same way, except now we're on that bottom corner. So we're going to have opposite be the square root of 3 and adjacent be 1. So sine of 60 degrees is square root of 3 over 2. Cosine is 1/2. Notice that those just swapped from the 30 degrees. So they just switched positions there. Tangent ends up being the square root of 3. And cotangent ends up being the square root of 3 over 3. Notice that those two just swapped. Secant ends up being 2 over 1, which is 2. And cosecant ends up being 2 square root of 3 over 3, and we see again that those two swapped. So if I can build my two triangles, my 1 square root of 2 triangle, which gives me 45-degree angles, and my 1 2 square root of 3 triangle, which gives me 60 and 30-degree angles, then I can put all those standard angles together and I don't need to memorize that table. And that's a good thing for me because I have a difficult time memorizing those tables like that. So now I have these, I'm going to take you to a drawn up unit circle. And this unit circle is available on Blackboard. You will find it on there. I think it's on the exams page. Don't quote me on that. So angles and points on a unit circle. So you can see that this goes through and it starts at 0 and it works its way. The inner circle gives you degrees. And then the next circle out gives you radians. And then the outside of the circle, you see the points as cosine x, well, cosine theta, sine theta. So those can come from those standard angles and quadrantal angles that we just talked about. But I want to point out something to you. Many times people get thrown off by this and they have difficulties transitioning to radians. And so they get reliant on a table, on a drawing like this of the unit circle. And I want to point out to you that I've already said I'm not good at memorizing things, but I can draw this unit circle without having to look at anything to do it. And the reason I can do that is because, first of all, I know the degrees. I've been dealing with them for decades, so that's not a concern. It's the radians that I don't deal with as often as I do degrees, so that throws me off a little bit. But I know that 360 degrees is 2 pi radians, which means that 180 degrees, which is half of 360, has to be pi radians, which means 90 degrees has to be half of pi, or pi over 2 radians. And 45 degrees has to be pi over 4, half of pi over 2, right? So I can do that. And then once I've got that, I can do all the 45-degree ones, multiples of 45 degrees, because actually at 0, I have 0 pi over 4. 45 degrees is pi over 4. 90 degrees is 2 pi over 4, which gives me my pi over 2. 135 degrees, 3 pi over 4. 180 degrees, 4 pi over 4. 225 degrees, 5 pi over 4. 273 degrees, 6 pi over 4. 315 degrees, 7 pi over 4. And 360 degrees, 8 pi over 4. So I can build all of those that way. Then to get my 30 and 60, I start at 90 degrees, and I know that's pi over 2. 30 is 1/3 of pi over 2. So 1/3 times pi over 2 gives you pi over 6. So if 30 is pi over 6, then 60 must be 2 pi over 6, or pi over 3. 93 pi over 6. 124 pi over 6. 150, 5 pi over 6. 180, 6 pi over 6. 210, 7 pi over 6. 240, 4 pi over 6. 270, 8 pi over 6. Sorry. Got myself out of my loop here. So 7 pi over 6, 8 pi over 6, 270, 9 pi over 6, 300, 10 pi over 6, 330, 11 pi over 6, and 360, 12 pi over 6. So I can just work my way through those. Then to get the x and y values, that's just the trig functions, and I can use my drawings to figure out all those trig functions. So I can build this if I need to. I don't have to memorize it. I don't have to necessarily look it up. But it can be easier at times to just look at it and go, oh, okay, that's what it is. and get it that way rather than having to go the long way, shall we say. And this will be available to you and you can use it on exams. I don't care. Okay, so let's look some more at trigonometric functions. For an angle theta in standard position, let P equal x, y be the point on the terminal side of theta that is also on the circle x squared plus y squared equal to r squared. Okay, so now we're not saying that we're on a unit circle. So the radius can be anything, so it's going to be r. So that makes our sine function, sine of theta is equal to y over r. Cosine is x over r. Tangent, y over x, where x obviously cannot be equal to 0 because then you'd have it divide by 0. Cosecant theta, r over y, where y is not equal to 0. Secant theta, r over x, x not equal to 0. And cotangent theta, x over y, where y is not equal to 0. Now, obviously, we don't put r not equal to 0 on these because if r is equal to 0, then you don't have a circle, you just have a point. So that's why we don't specify that, because r has to have some value for it to be a circle. And that finished up section 2.6.2, getting us ready for next time for properties of trigonometric functions.